Okay, this next lesson is about related rates, and we're just going to talk about the different kinds of problems you have with related rates. Here's just an example, and you don't have to write anything down for right now. I just want you to listen and watch the problem. Here's an example. An observer is tracking a plane flying at 5,000 feet. So here's my observer down here. Let me get a pen. Okay, so the plane flies directly over the observer on a horizontal path at a fixed rate of speed dx dt. That's what they're calling it. As time goes by, the distance from the plane to the observer changes. What is the rate of change of the distance yt? So I'm finding dy dt, the rate of change of my distance y. Units are in thousands of feet. So I just want you to see what the problem looks like. Don't worry about the numbers or what anything is being called. Here's my observer. Here's my plane up here. It's a 5 right there because it says 5,000 feet up. So my plane is directly overhead of the observer and is moving to the right. So here's my plane. And as you can see, here's my observer, here's my plane. As the plane moves, the distance from the observer to the plane also moves. And they're wanting to know what is the rate of change of that distance. So how fast or slow, how fast is that rate of change happening? So remember the key word here is rate of change. So we automatically know that rate of change will be talking about derivatives. Okay? And when we're doing related rates problems, we're going to be doing implicit differentiation because instead of taking the derivative with respect to x, we're going to be taking the derivative with respect to time. So we're always going to be finding the derivative, but we're going to have to use implicit differentiation. So this is one example of a related rates problem with a plane. Okay, let's look at another one. Okay, a building supply company is offloading sand from railway cars using a conveyor belt. The conveyor belt moves the sand up an incline at a fixed rate and spills it into a pile. The pile is conical in shape and changes size as more sand is dumped onto it. By observation, it was noted that the height of the pile is some constant times the radius of the circular base. So look, we're just going to look at the picture. Here's my belt with sand going up. Here's the sand falling. As the sand comes up and falls, it's forming this cone. Okay, as more sand falls, my cone is going to get bigger and bigger and bigger. Okay, and pretty soon they're going to show you different pictures. So here's when my sand first starts falling. It's getting bigger and bigger. If you'll notice, the bottom of my cone is getting bigger as well as my height, or we'll say the radius because it's a circle on the bottom. So that's another example of a related rates problem. Now I want you to look at your notes that I gave you. Most related rates problems can be solved with the following 5-step process. So the very first thing we're going to do every time is sketch a picture of it. A lot of times we'll be sketching a triangle, sometimes it'll be a circle, but you always have to sketch a picture. Okay? When you sketch a picture, you want to label it, and we're going to pick logical letters to represent what we're looking for. So for example, if we're finding the radius, use an R for radius and not an X. So I want you to highlight or underline that first step, sketch and define. The next one, number 2, is symbolize. So highlight that or underline it. One key to solving related rates problems is to be able to symbolize. For every related rates problems that we have, on our work, we are going to write these 3 things down. We're going to say find, and then we're going to fill in the blank, when what, given what. And each of these 3 things will be written on every single problem. The first one is find. That's what they're going to say. They're going to say find the rate of change of something. Okay? And it's usually a differential quantity like dy dt or dx dt. It's always going to be written as a rate of change of something. When is going to be a point in time. So it might say find the rate of change of the radius when time equals 4 seconds. So we're going to have a when in the problem. It's always going to be a time. Given is also going to be a rate of change. Okay, usually a differential equation like dv dt or something like that. And once we start doing examples, you'll understand more what I'm talking about. Step 3, write the equation. We're going to write the equation, and usually it's going to be either from one of these three sources. A trig equation, like a trig identity, a Pythagorean theorem, or some kind of formula that they give you, like a volume formula. Part B, for some problems you may have to modify the equation you wrote in step A. The equation must contain only the variables that we wrote in the find what, when what, given what. And I'll show you examples in class. Step 4, we're going to find the derivative. All rates are taken with respect to time, so implicit differentiation is needed. Okay, so for example, if I had, let me get my pen, okay, and just write this down someplace on your paper. If I have v equals 2t, that's not a very good example, but I said find the derivative with respect to time. The derivative of v is derivative of v with respect to time equals, and the derivative of 2t will just be 2 because my t's match up. Okay, if I said area equals pi r squared, and I said find the derivative with respect to time, the derivative of a would be dA over dt equals, okay, this is the power rule, so I bring down my exponent, 2 pi r, okay, but I have r as my variable, not t, so I need to say times dr dt. Right, so that's what I mean when I say all rates are taken with respect to time, so implicit differentiation is needed. If I'm finding the derivative and it's anything other than a t, I have to write that dv dt down, or dr dt. Okay, and then step 5, solve and substitute. And once we start looking at examples, you'll kind of know more what I'm talking about. All right, so here's the first example, and we're just going to do part A. I know you don't have this on your sheet, so somewhere on the bottom of your sheet, I don't care which part, but somewhere on the bottom of your notes, we're going to do this part A together really quick. And then there's a part B and part C, but we're just going to do part A together. So it says, a 12-foot ladder leans against the side of a house. The base of the ladder is pushed toward the house at a rate of 2 feet per second. When the bottom of the ladder is 3 feet from the house, find how fast the top of the ladder is moving up the side of the house. So very first thing, part number 1 says, sketch and define. So I have a 12-foot ladder. Here's my ladder, and I know it's 12 feet. And it's leaning up against the side of a house. There's my house. Okay, it says the base of the ladder, so this right here, is being pushed toward the house at a rate of 2 feet per second. Then it says when the bottom of the ladder is 3 feet from the house, find how fast the top of the ladder is moving up the side of the house. All right, so step 2 says to symbolize. This is where we're going to write our find what, when what, given what. Ooh, that doesn't look very good, but that's okay. So find what? So they said find how fast the top of the ladder is moving up the side of the house. I'm going to label this. I'm going to label this Y, and I'm going to label this X. Okay, so I want to find how fast Y is moving. So anytime Y is moving or it's changing, I'm going to say that that is dy dt. That's what I'm finding, the rate of change of Y. When, and it says when the bottom of the ladder is 3 feet from the house. So the bottom of the ladder, is my x value when x is 3. Given, now given is always some kind of rate. So let's see what it says. 12-foot ladder. The base of the ladder is pushed toward the house at a rate of 2 feet per second. So my x is changing 2 feet per second. And do you see that it's being pushed towards the house? So my rate, this is getting smaller and smaller. So it's actually going to be a negative 2 feet per second. So given dx dt is negative 2 feet per second. Okay, so that's all I wanted to do for this problem in the video. Okay, is to do the sketch and then to write down the find what, when what, given what, and then we're going to finish this in class. All right, so I'm going to be checking if you have these down, and then when you're finished watching the video, I want you to email me saying that you have finished watching the video. Okay, my email address, johnny.edsel@tulsatech.edu. All right, so short and sweet. Make sure you have this written down and then just send me a video saying I've watched the video and wrote down the first part of number 1A. Okay, I'll see you tomorrow.